Welcome to today's presentation, Stepper versus Servo, Understanding the Differences. Our goal today is to provide basic understanding of the differences between the two motor types and when to apply them in your application. We will begin our discussion by reviewing some of the motor basics such as construction and basic principles of operation. With that knowledge, we will step through some of the basic criteria for selecting a motor to determine when to choose a stepper and which applications are best served using a servo. We will do a run-through of a couple of applications as practical examples of the motor selection process. Finally, we'll wrap up with a quick review that will include some key terms that will help you with future applications. Let's start by taking a look at a stepper motor. Most industrial stepper motors are hybrid stepper motors that consist of a permanent magnet rotor and a wound electromagnetic stator. As you can see in the image, the rotor is constructed of two sections referred to as cups. These cups have teeth of uniform spacing ground into them, typically 50 teeth. This is where we get the poles of the motor from. These two cups are aligned so that the teeth are offset by a certain amount. The entire rotor is magnetized so that one cup is polarized north and the other is polarized south. Now when we look at the stator, we see it also has the same tooth construction. It is this tooth construction that gives us the individual steps of the stepping motor. DC current is used to energize the magnetic coils of the stepper motor. To energize the electromagnets of the stator windings, a DC current is applied to the stator. This will energize the magnetic coils of the stator, causing the rotor to align to the magnetic field of the stator. This DC current is applied to the motor from a stepper driver. The stepper driver controls the current level and the rate of change within the stator windings. Let's take a closer look at what happens when the current is applied to the stepper motor windings. The current supplied from the drive creates a magnetic field that is used to rotate the shaft of the motor. Let me begin by saying this is a very basic approach, but the same principles apply to modern stepper motors. In step 1, the upper electromagnet is activated and the teeth of the central cog line up accordingly. The electromagnet in step 1 is deactivated and the right one is turned on. The closest cog teeth then jump to line up with this. This causes a step of 1.8 degrees. Next, the right electromagnet is deactivated and the lower one is turned on. The cog teeth then jump to line up with the bottom electromagnet. This causes another step. The bottom electromagnet is deactivated and the leftmost one is turned on. The cog teeth then jump to line up with this. This causes another step. On a motor which has a step angle of 1.8 degrees, which is a typical industrial stepper motor, 200 steps are required for full rotation. Below are some other basic stepper motor facts. First being that microstepping increases the number of steps per turn. Instead of just turning the motor phases full on and full off as we do in the previous examples, with microstepping, we ratio the current going to the motor windings. This allows the rotor to line up within the poles of the stator, making smaller and smaller steps. This provides more precise control and smoother motion of the stepper. Also, increasing the current increases the motor torque. When we increase this current, we need to be aware of the motor current limits. If we exceed that motor current limit, we can overheat the motor and, in worst case, demagnetize the rotor. The higher the step frequency, the higher the motor speed. As motor speed increases, back EMF within the motor can reduce motor torque. We can overcome this back EMF by increasing the voltage to the drive, by selecting a higher DC voltage drive, or selecting an AAC motor drive. No position feedback is required. However, it is optional. With a stepper, we can select either an incremental feedback or multi-turn absolute feedback to help provide position verification and stall detection. To summarize some of the basic facts of a stepper motor, DC current generates a magnetic field. It is an open loop constant current system. and current is maintained while the motor is at rest. Some of the advantages of a stepper include simple design and control. There's no feedback required. It has excellent low-speed torque and low-speed smoothness. Its simple design and no need for feedback leads to a lower overall system cost. Some of the disadvantages are that torque decreases as speed increases due to the back EMF. It is a constant current device regardless of the load requirements, and it cannot react to changes in the load. Some fun facts. Did you know that in 1920, the actual application of stepper motors began? A variable reluctance type stepper motor was used by the British Navy as positioning control and remote control. Now let's take a look at some of the servo motor basics. Let's take a look at the basic servo motor construction. In an AC servo, as you can see in the image, there are three stator windings referred to as the A phase, B phase, and C phase. For the rotor, we have permanent magnets similar to the stepper, but the rotor has a much lower pole count, typically 4 to 12 poles. In addition, the servo motor will have position feedback, such as an encoder or resolver that will be used by the servo controller to properly control the motor current. The above image illustrates how the current is phased through the three windings of the motor. As the current flows through the stator windings, a magnetic field is created relative to the phase current. The feedback from the motor is sent to the servo drive, and the servo drive adjusts both the current level and current frequency based upon the feedback coming from the motor. Here is a basic illustration of what occurs within the motor. As each phase changes, the magnetic field changes, resulting in what can be referred to as a rotating magnetic field. As this magnetic field changes, the rotor will follow, keeping the rotor magnets aligned with the stator's magnetic field. Other things to know about basic servo technology. Increasing the current increases the motor torque. The higher the current frequency, the faster the motor will rotate. Servos monitor and regulate the motor current for more precise torque control, and motor feedback is required for proper current control. To summarize a servo motor's basic operation, three-phase AC current generates a magnetic field. It is a closed-loop system that continuously monitors position relative to commanded position and adjusts current accordingly. A motor brake is required for zero-speed holding torque. Some of the advantages of a servo are: it has closed-loop control. It can provide higher torque at higher speed because of the lower motor pole count. It has lower motor heating and is a better choice for variable load systems. Some of the disadvantages are that it has a more complex control, which means tuning is required. Position feedback is required because of the closed-loop system, which leads to a higher overall system cost. Did you know a camera's autofocus uses a precise servo motor built into the camera that corrects the position of the lens to sharpen autofocus images? Oftentimes when I'm helping a customer select a motor, they often start with the motor type already selected before they really understand what is required. Think back at the last few motion applications you worked on. Did you select the motor based on design criteria or habit? Did you select a servo because it was what you always use? Do you select a stepper only for simple applications? This section will help you understand the questions you should ask to find the best motor for your application. Here you will find a good start on some of the questions you should be asking when deciding which motor technology is best for your application. What is the load I need to move? What are the speeds I need to run at? Does my load vary throughout the move? Are there any special functions I need, such as holding torque or torque limiting? Also, what is my budget, which would lead us to a conclusion of which motor is best for my application. Let's start by looking at what is the load that I need to move and what are the speeds that I need to run at. When we start our application, the first thing we want to know is how much load we need to move, and that is the torque we need from the motor. Let's assume our application requires 150 ounce-inches of torque. When we select a motor for an application, we need to know how much torque the motor can supply. For this, we'll use a motor torque curve. Here is a typical servo motor torque curve. As you can see, the servo motor we've selected will provide enough torque for the application. Let's overlay a stepper motor torque curve on that of our existing servo. It is often assumed servo motors outperform steppers of equivalent size, but this often is not the case. Here is an equivalent size stepper motor torque curve compared to the servo torque curve. This is why understanding the speeds we need to run out is very important. As you can see here with these two torque curves, at speeds up to say 1500 RPM, either one would work well. At speeds below say 1200 RPM, the stepper might be a better choice. That's why we can't just assume, oh, I want to use a stepper, or oh, I want to use a servo. Both torque and speed are a necessity when it comes to deciding which motor is a better fit. Here is where understanding the two different motor technologies is paramount. As you can see, at high speeds, the stepper motor torque approaches zero, while the servo motor provides consistent torque throughout the entire speed range. For the two motors selected, the servo can provide that 150 ounce-inches of torque we asked for at speeds beyond 3000 RPM. It is this back EMF that we're fighting with the stepper that is causing that torque to drop off, which is why for applications above 2000 RPM, we often focus our attention on servo motors as the right choice. Another consideration when deciding which motor technology is best is understanding, does my load vary throughout the move? On the previous slides, when we were looking at the servo motor torque curve, what we were looking at was what's referred to as the servo motor's continuous torque, or RMS torque. This is the area in which the motor can operate continuously without overheating. The servo motor has the ability also to provide what is referred to as peak torque. The peak torque area is an area in which the motor can operate temporarily to overcome changes in load or overcome high accelerations in the motion profile. When operating in this area, we need to take care that we don't operate above continuous torque and below peak torque for long periods of time. If we do, we can overheat the motor, causing damage to the system. Another question you may want to ask yourself is, are there any special functions I need, such as holding torque or torque limiting? One of the features that separates the stepper from the servo is the ability to do what is referred to as holding torque. Stepper motors can provide full torque at standstill while the windings are energized, holding a load against an external force while the rotor is not rotating. This is referred to as the holding torque. This feature makes stepper motors a good choice for cases where a load needs to be held in place. Let's think, for example, a lane diverter. When the lane diverter is at rest, we want to make sure that it stays in position and doesn't move around. This may cause products to jam. Because the stepper motor has a holding torque, as product bounces against that lane diverter, it will not move, keeping everything in place and operating as normal. A feature that can be useful for servo motors is the ability to do what is called torque limiting. Servo motors can control motor torque through the precise monitoring of the current provided to the motor and limits it so a specific torque value cannot be exceeded, thus referred to as torque limiting. With the advantages of torque control, many applications that require precise force control for pressing, pulling, and twisting motions can be accomplished. Let's think, for example, two-part assembly, and those two parts are press fit together. By using a servo to control that motion that pushes the two forces together, we can precisely control the amount of force applied to make sure they snap fit tightly and securely to the proper amount of force. We can also monitor to make sure that we reach the proper amount of force, and if that proper amount of force wasn't achieved, we can understand that those parts weren't assembled correctly and reject them as necessary. The next question you should ask yourself is, what is my budget? Let's look at the cost difference between the two motor solutions. Stepper motors typically don't require feedback, use less expensive magnets, and rarely incorporate gearboxes. Because of the high pull count and their ability to generate holding torque, they consume less power at zero speed. As a result, a stepper motor is generally less expensive than a comparable servo motor. Servo motors require feedback, use more expensive magnets, and often incorporate gearboxes. They also consume more power at zero speed. As a result, a servo motor is generally more expensive than a comparable stepper motor. With the information gathered from the above review process, we can now decide which motor is best for my application. Let's take a quick look at some of the features and functions that each motor can provide. This will help us decide which motor is best for our application. Stepper motors and servo motors are controlled in quite a different manner. A stepper motor is an open-loop system, while a servo is a closed-loop system. Review your application needs to determine if one control method provides features that set it apart from the other. So let's compare the two motors. When considering application requirements, there are several parameters that need to be considered, and the chart below provides a good starting point to help guide the designer to the more appropriate technology. Do we need position feedback? If the answer is no, we might want to start with a stepper as an option because no encoder feedback is required because it's an open loop system. If position feedback is required, both a servo and stepper can provide it, but with a stepper we would have to add those components as either an incremental or multi-turn position feedback. Do we need holding torque? If we do need holding torque, the stepper would be the right fit because it's part of the stepper motor's operation. Whereas with a servo, to have holding torque at rest, we may need to add a motor brake. Do we need torque control? If we need torque control, the servo would be the logical choice because this is not a feature often found within a stepper control system. Do we want to simplify control? If we do, the stepper's open loop system is a much more simpler operation than a servo. With a servo, our control loop needs to be tuned to maximize operational efficiency. Do we need to support dynamic load changes? If we do, the servo would be the better fit for those types of applications. If we're looking for low speed operation, the stepper would be a better fit. If we're looking for high speed operation, we may want to start looking with a servo. So when would I choose a servo solution? Consider using a servo when your application meets any of these requirements. High speed is required, certainly anything above, say, 2000 RPM. Dynamic motion profiles, such as very high accelerations or dynamic load changes, or you need to control the applied force. Benefits of the servo include torque control. They can execute complex motion commands. They can adjust to changes in load and lower power consumption. So let's take a look at a couple of applications. First, let's look at a stepper application. For this application, we're looking at doing an automated roller adjustment. The manufacturer is looking to automate roller setup. The goal is to reduce changeover time and increase repeatability between various product setups. The application requirements are that we need to integrate into an existing PLC control, the cycle time of under 1 minute, make micro adjustments on demand, monitor position, and we need to hold position while we're at rest. Although both motors can accomplish the application, based upon the requirements that we were asked to meet, the stepper is a better choice. Both can operate at low speed, but the stepper has better low speed smoothness than the servo. Both can connect to the PLC for control, so that's not an issue. The stepper has holding torque. To achieve that function with a servo, we may need to add a brake, which would add cost. Both can do position verification with the addition of a multi-turn feedback encoder to the stepper. The lower overall system cost makes the stepper the better choice. Now let's look at a servo application. In this application, we're looking at a bottle capper. The OEM builder of filling and bottling lines needs a linear and rotary actuator as part of an update to a capping operation. The goal is to place the cap accurately and report any missing or misapplied caps. The application requirements we've been asked to meet are: integrate into existing PLC control. It needs to have a very high throughput. We need to have the ability to limit cap on torque. And we need to be able to manage multiple products on the assembly line. For this application, the servo is the correct choice. The servo's closed-loop control allows for better monitoring of motor position and current control. Torque limiting of the servo gives the system the ability to precisely apply the caps to correct cap-on torque. Because it is the only solution that can do torque monitoring and has a higher throughput, it makes it the obvious choice. Whether you're looking for a servo solution or a stepper solution, AMCI has the right product. Our integrated motor product families provide a complete solution by incorporating the motor, drive, and controller into a single package that offers the simplest installation possible. Whether you're looking for integrated servo motors or integrated steppers, AMCI has exactly what you need. The next two slides here contain some key terms that you'll run across when working on motion applications and selecting motion products. I'm not going to read them all here for you. They're here for you to read at your leisure. But one I do want to highlight, because we mentioned it a few times in the slideshow here, is that of holding torque. And when we're referring to holding torque, what we're referring to is the maximum external force or torque that can be applied to a stopped, energized motor without causing the motor to rotate continuously. Another one we talked about when we're looking at torque curves would be that of rated torque, which is the torque producing capacity of the motor at a given speed. This is the maximum torque the motor can deliver to a load and is usually specified with its torque speed curve. In addition to today's webinar, we have other products that are available to you from our website. We have tutorial articles, brochures, and other educational webinars that we've produced earlier. If you need support directly from AMCI at the factory, there are numbers here of the individuals that can provide that to you. Matt is the applications engineer, and Jeff is our tech support. Thank you for watching today. I hope you found this presentation valuable and informative.